Let's discuss about the major and the minor losses in pipes. So let's first see what is called as the major losses. Well, major losses occurs due to the viscosity of the fluid and basically due to the fluid friction. Okay, and how do we quantify this? We have already seen the Heisenberg equation derivation and how we convert that into Darcy-Weisbach equation. So the standard way to quantify head loss, the major head loss in pipes is by this FLV square by 2G where F is your friction factor. It depends on, lot many things, type of flow. If it is laminar flow, it is 64 by the Reynolds number, and if it's turbulent, it depends apart from apart from the Reynolds number, it depends on the geometry and other stuff, surface roughness. So turbulent is all complicated. Most of the time we assume it's laminar, and when we use this, L is the length of the pipe, V is the mean velocity or the average velocity. So how do we get this? We take the total flow divided by the area of cross section. That's it. G, G is the gravitational acceleration and D is the diameter of the pipe. So this is something which we have derived already, and this is the standard form. Head loss we use, and this equation is also called as Darcy-Weisbach equation for major loss. Okay, now what about the minor loss? So minor losses, first see why they occur. Now minor losses, all the losses which occurring due to sudden enlargement or contraction of the pipe, the basic idea is to changes in the geometry, sudden change in the geometry along the flow. So that's so all those is classified minor losses. So let's see some important types in this. So loss of head due to sudden enlargement. Okay, so if you have sudden enlargement, let's say the flow is taking place in a small diameter pipe, and then there's a sudden change, and now it has to follow a larger cross section pipe. So if you would have, if you would have seen how the flow occurs, it will just follow this, and then because of the sudden change, it's unable to follow the pipe geometry. It will just take some time, or after some portion of the pipe, it will just come and follow the path, follow the diameter. So in this region, you'll have some kind of a eddy formation. Okay, along in the corners, you have the eddies formation, and that is not your perfect flow. That's laminar flow, and the flow in these eddies formation is kind of a rotational flow. It's not irrotational. It's rotational flow, takes away some energy. Near the corners you have all this phenomena due to the sudden change in the wall. Head loss in this, well, can be derived from, because you need to know the pressure in this eddies formation, and then from all the impulse momentum consideration and from the energy loss, by applying Bernoulli's plus impulse momentum equation, we get a final expression of the head loss occurring something like this, v1 minus v2 whole square by 2g. So this is after a long derivation, but typically we don't, I'm not deriving that, you just we need to just uh, so this is how it is quantified. Okay. Okay. And then if you have sudden contraction, loss of head, loss of head due to sudden contraction. Well, the initial was sudden expansion. Now flow is taking place in a larger dia pipe, and suddenly you ask it to follow a smaller dia pipe. So what happens? It follows, but just it takes, when the cross section change takes place, it can't follow the sudden change. Okay, so there is some kind of post cross section change, there's some kind of an eddy formation, and then after that it follows. There is some kind of, in this region there is some kind of eddies formation. So let's say upstream the velocity is v1, downstream it is v2. So here there are many things. Head loss is just classified as k times your final velocity whole square by 2g, but then k depends on the area of cross sectional change, and most of the time it is represented like this by a factor cc. Cc measures how much, what is the area of cross section here and what is the area of cross section here. That ratio is what cc matters. But generally what we do is we take point k as zero point 0.5 times the final velocity whole square by 2. Final velocity means the downstream in the smaller pipe whole square by 2. So now the next is loss of energy or loss of head at entrance to a pipe from a large vessel. So you have a large vessel and now it's entering a smaller dia pipe. So this is just similar to just the case B, where the flow is entering from a large dia to a small dia. So this head loss is just similar. Only thing is, so this is just similar to your larger to a smaller. Only thing is this is very large. This is similar to your tank dia. So the head loss is just quantified in the same way, 0.5 v square by 2g, where v is the velocity in the pipe. Okay, and then exit from a pipe. So exit from a pipe. So how do you handle this situation? So you have pipe, now it's exiting to a larger tank. Let's say, so this is similar to case, similar to the flow entering from a smaller dia pipe, entering from smaller dia to larger dia pipe. So this we have seen in the case A. Okay, and there it was v1 minus v2 whole square by 2g. Obviously this was v1, and well, as the cross section is very large at the second, so you can neglect the velocity. So v1 minus v2 whole square by 2g. So we take it as v square by 2g, where v is the flow, velocity of flow in the pipe, and now for the exit we quantify this is the loss. So these four are the important things, and any other, like let's say, okay, so these four are your normal thing. Okay, and then if you have set, let's say you have a bend, some kind of a bend, it depends on the radius of the bend whether it's smooth or sudden bend, all that. So all this flow in bends, we quantify the head loss by just k v square by 2g. So v square by 2g is just standard term. This k depends on how smooth the pipe is. how smooth the transition is in the geometry. So this is the general way, k v square by 2g. This is how we quantify. We have seen major losses, minor losses. Major losses main is because of friction which occurs along the length of the pipe, not because of the geometry change but because of the fluid friction. And because of geometry changes you have all these minor losses. These minor losses are small when compared to your major losses values. Okay, so now let's take, if say you want to transmit, now considering all these losses, let's say you want to, you have a bigger reservoir somewhere at height and we want to transmit or transfer water to a lower reservoir which is situated somewhere below the height. Okay, this is the mean level, let's say reference. The water level in the bigger reservoir in the one is here, let's call it A, let's call it B. Okay, and this is where you have connected the pipe. So this height, let's say given is HA, height in the height of the water in the tank, and this is your ZA. So HA plus ZA is the total height from the ground level, let's say. And here, let's say the water level is up to here. So this height is HB and this height is ZB. And let's say the velocity of the flow in this is V and the length of the pipe is L. Okay, so now if I apply Bernoulli equation from point 1 to let's say point 2, okay, so at point 1 the pressure is atmospheric, so atmospheric pressure by rho g plus the velocity here, okay, plus the velocity here. So velocity here, because it's a very large cross section, so I neglect the velocity plus the height from the mean. So if I take this as my reference level or the ground level, so this will be your HA plus ZA is equal to, at this point, I'm applying between the Bernoulli equation between the free surfaces. So this is 2 rather than this is 2. The free surface here is 2. I'm applying between 1 and 2. Okay, so at 2 you have atmospheric pressure again plus velocity. We neglect, we consider the both the reservoirs are of very larger dia, so velocity changes. Height is HB plus ZB. Now plus if you have head losses in between, so the total head loss, let's write down HL. So this equations become HA plus ZA is HB plus ZB plus the head loss that is occurring throughout the flow. So now identify what is the head loss that is occurring throughout the flow. Now here you have a sudden change and it's exit from the pipe. It's basically the case C where there is an entrance to the pipe from a larger reservoir. So we term that loss as entrance loss or head loss of head at entrance to a pipe from large vessel. So that is 0.5. Let's say velocity is v here, so 0.5 v square by 2g is the loss that is occurring due to entrance. Now due to the viscosity throughout the length of the pipe you have the head loss, and that is FL v square by 2g t. And now because of the exit from the pipe you have the head loss which is v square by 2g. So there are three losses. One is due to the entrance change in the geometry. This is due to along the length because of viscosity, and this is at the exit. So the entire equation can be written as HA plus ZA minus HB minus ZB is equal to your 0.5 v square by 2g plus FL v square by 2gd plus v square by 2g. So this, let's say, is the difference in the heights of the difference in the levels of the reservoir from the mean surface level, and that is your v square by 2g 0.5 and plus 1. Okay, and this is FL by d plus 1. This can be written as v square by 2g 1 plus FL by d. V can be written as your in terms of Q. So V is volume flow rate by Q, which if it is circular, pi by 4d square. So Q square by 2g pi by 4 d square whole square into 1 plus FL by d. So one thing is, so there are a couple of things point here. First is difference in the liquid surfaces in two reservoirs at two ends of the pipe is equal to sum of various head loss. That is clear from this statement, right? The difference in uh, the free surface or the reservoir levels is basically the sum of the various head losses. So another equation, another point which comes from this is, for a particular value of H, or for a particular value of the head loss or the difference H, you have value of flow rate Q. So that means for a given, like if I know say one reservoir and the other reservoir downstream, I know the flow levels, okay, from the main surface, know the difference in the free surface levels, the difference in the height of the water in both the reservoirs. And if I am using a constant dia pipe, then I know that I can supply flow up to a limitation. So that is the limitation here. So flow rate is fixed. So for a given H and for a given dia pipe, the flow rate is fixed. So I can know how much quantity of water I can transfer per second. So that comes from this equation. So this is how basic Bernoulli equation can be applied. So only thing extra apart from Bernoulli equation which we have learned is how to quantify major and minor losses and how to apply them in the general energy balance equation. Okay, so now sometimes you may have, instead of having straight pipes, you may have siphon. Okay, so water siphons. Sometimes you may have a hill in between or a mountain in between the two reservoirs. So what you do, you bend the pipe. You don't use a straight pipe. So you use, let's say, so here somewhere here you have a mountain. So what do? You bend the pipe to a very, very larger. Let's take it till here and then transfer the pipe. So the pipe is not straight because of the obstruction somewhere in between. You lay the pipe in this way. This is how you lay it. Okay, so this is, let's say, your water surface here, and let's say water surface here, and let's call, okay, and this height from the surface reservoir A, this height is H. So the analysis is similar when you are applying between two reservoirs A and B. Whatever we have applied in the previous way, same way you can apply. So remember, siphon is used when you have mountains or hills present where your straight pipe is difficult to use. So that's where you use mountain. So now the head loss, the total head loss, which we can find out just similar to what we have done in the same way. we can apply head loss and we get 0.5 v square by 2g because of the entrance loss. And throughout the length of the pipe, say the total length is L, so FL v square by 2gd plus your v square by 2g, because so this L is length of the siphon. So if it is curved, it is curved, that's it. V square by 2g is the exit loss. So this is how you apply the total head loss. Apart from this, what else matters is when you are applying from here to here, okay, let's say point 1 to point 2, top of the siphon. At 1, let's apply Bernoulli equation between 1 and top of the siphon, just point 2. So at 1 the pressure is PA by rho g, okay, and this only if I take the reference level. Velocity is 0 because larger diameter pipe. This only if I take the reference 0, so the height is 0. At 2, let's say the pressure is PS, it's in the pipe, so I can't put it atmosphere, so PS 0. Velocity of the flow is v square by 2g, height is h, plus head loss from 1 to 2, you have this entry loss, so 0.5 v square by 2g, and at this point, and this length, let's say this length might be small l, so due to that length of the siphon from 1 to 2, that length of the siphon is small l, so f small l v square by 2gd, that's it. This is the head loss due to entry and due to that small l. So now this PS from this equation is less than PA, because these are non-zero positive terms. PS will be less than 0, but there's a limitation. PS can't be below PA. So the limitation for PS is that the pressure is less than atmospheric. And one thing we should have to take care is that it should not go below the saturation PSAT pressure, the saturation pressure at the temperature, at the operating temperature, so saturation temperature at operating temperature, because if it goes below the saturation temperature at operating temperature, typically if it is 25 degrees Celsius, okay, the saturation pressure is 3.98 kPa, okay, and atmospheric pressure is 100 kPa. So if PA is 100 kPa, PS is less than 100 kPa, but we have to make sure that 100 kPa is the atmospheric pressure. That is default, but PS will be less than 100 kPa, but it shouldn't go, let's say if the temperature is 25, it shouldn't go below 3.98, because if it goes below, then there's a chance of cavitation if it goes below. So cavitation, well, if the pressure goes below the saturation, if the pressure goes below the saturation pressure at operating temperature, then it will create, the vapors, it cannot be in equilibrium, it converts into vapor, and those vapors will collide with the walls and bursting, leading to higher pressures, damaging the wall surface of the pipe. All those things occur, so we don't want that case. So you have to always keep a cap on this hedge. Hedge shouldn't be very high, such that PS falls significantly below atmospheric pressure. And whatever example I gave, from falling from 100 kPa, 100 kPa is PA, but PS will be less than 70, 80 is okay, but it shouldn't go, let's say, at 3.98, because if it goes, it will collide, vapors will form, cavitation may occur. Cavitation has a lot of effects. It deteriorates the performance, as well as the wall surface will erode after some time. So that is one important thing which you need to consider when you are designing this hedge. It should be it should be, or this H should be, I mean, you have to take care that this quantity is not significant. So H shouldn't be as high as possible. So that is one thing which we analyze while dealing with siphon. So this is all about flow through pipes. Apply the basic Bernoulli equation along with the proper head losses, major and minor. Thank you.